welcome back to day 2 of lecture from my quarantine. So today we are going to go through another gas law. It's called the combined gas law. This one is just going to put together everything we learned yesterday with Boyle and Charles. So if you weren't here yesterday, hopefully you can get a paper and then you can watch the lecture from yesterday on Schoology and do some of that. And then today piggybacks off of that law. And today isn't that much harder. We're just going to add another layer to it. This is going to be a really short lecture because each of these little lectures with the gas laws goes with a series of demonstrations I would do if I was there, where we have what are called Maddenberg hemispheres and water bottles and darts and things like that. So we will get all those demonstrations done when I can get back, but we are still looking at a quiz on Friday just over these gas laws. So hopefully I'll be back and we'll be all kicking and knowing how to do this stuff. One thing I do suggest is either pass out this note worksheet, or if you are in my third period, go ahead and get out your packet. You should have this in there. And also while you're getting some stuff out, like a calculator, go ahead and get out your periodic table. You're going to want to write these on the back of your periodic table so that you can have them as a reference sheet. I'll let you use it on your quiz on Friday, so you can have Boyle's, Charles, and combined gas laws. And then so you don't have to memorize these, but you will have to know them for the test. But for the quiz, I'll let you use your periodic table. So just a little bit, and you do need a calculator because, again, we're quantifying these changes in variables in gases. So just a refresher from yesterday, and I still have my same crummy mouse. We're going to try, see if we can't do a little better here. So volume is always measured in liters, and the unit is L. And so that's what you'll put on your final answer, and that's what you will read when you're reading a number that is measuring the volume. And remember, you move your decimal 3 times to the left in order to take it from milliliters to liters. So if somebody says you have 200 milliliters, you know that's really 0.2 liters. Pressure, we said, is measured in atmospheres, or ATM. There's lots of different ways you can measure pressure, PSI, different things, but we are just going to use atmospheres, and 1 atmosphere is sea level. Temperature is going to be the one that we're usually going to forget to change here. We need to measure that in Kelvin, and the shortened unit for that is K. And we're always going to take our any degree Celsius we've been given, and we're going to add 273 to get our Kelvin on that. And Kelvin is because of the absolute zero scale. Just a good refresher over yesterday. Boyle's law is P1 V1 equals P2 V2. And Charles' law is V1 over T1 equals V2 over T2. So what that means is Boyle's law says when we increase the external pressure, okay, and this is external. Oh, we're going to start with decrease. When we decrease the external pressure, our volume can increase. And we talked about bubbles in a pool and how they rise from the bottom to the top. And then the difference, when I increase the external pressure, I can make the volume come down. Charles' law has to do with volume and temperature, and they go up and down directly with each other. So if you increase the volume of a gas or temperature of a gas, you increase the volume of a gas. And if you decrease the volume of a gas, decrease the temperature, you decrease the volume. That sounded awful. Arrow up, arrow down, arrow down. All right, so now all we're going to do is we're going to take these two. You can probably see a whole lot of similarities between them. And what we're going to do is we're just going to move and put them all into one. So P1 times V1 and then V1 over T1 can lead us into what's called the combined gas law. And so that's P1 V1 over T1 is equal to P2 V2 over T2. And the way I remember this one is the potatoes, P, and the vegetables, V, go on the table. So I think yesterday I was talking about how the veggies go on the table for this one. You don't put the table on the veggies, but the veggies go on the table here. So now the potatoes and the veggies go on the table for the combined gas law. And again, if you want to take a minute at some point in time today and write that on the back of your periodic table, you should have a spot for that one as well. So we do also on the back of your periodic table and here on these notes want to point out that there are some special variables. This is called STP, or standard temperature and pressure. When the science community is working with gases and things like that, there are a set of standards that they hold to. So it's almost like just making sure everybody's measuring in centimeters instead of inches, because you want to be able to compare stuff. So standard temperature, when you're dealing with gases, if you publish a paper, you say it's a standard temperature, that would be 0 degrees Celsius, but we're going to say that is 273 Kelvin. So it's basically gases are manipulated at freezing, and which is 273 Kelvin. And then standard pressure is sea level, which is 1 atmosphere. 1 atmosphere or sea level. So whenever a problem says, hey, this gas is at STP conditions, you know that your temperature, T, is 273. Where's my highlighter? Boop. And then your pressure is 1. So you can just plunk these right in whenever you have something that says at STP conditions. So let's go ahead and have whoever is running this class to go ahead and pass out worksheet number 2. All right, so here we go. What is the equation for the combined gas law? That's P1V1 over T1 is equal to P2V2 over T2. Pressure, atmospheres, temperature, Kelvin. Remember, you add 273 to Celsius. And then volume is in liters, and you got to move 3 times the decimal to get it from milliliters to liters. STP is standard temperature and pressure. There we go. I'm probably going too fast. I'm going to slow down. It's hard when nobody's talking to me. And standard temperature is 0 degrees or 273 Kelvin. And standard pressure is 1 atmosphere. So now we got to read through, and again, these turn into little reading problems, so we want to make sure we know what's going on. A sample of neon gas has a volume of 83 liters, which I like that number, that's good, at 25 degrees Celsius. Not digging that number. We're going to have to change that once we get in here. And at 0.5 atmospheres. Nice. What will the volume be at 100 degrees Celsius and 1 atmosphere? So sometimes what I like to do when I'm reading is I like to go through and put the variables on here. So this is a volume. That is not going to work because that's a highlighter. This is a volume. This is a temperature. And this is a pressure. Yes, mouse. All right. What will the volume be? That's my question mark. At 100 degrees Celsius. Again, don't like that number. That needs to be 373. And so that's going to be my temperature. And then this is my pressure. So when I see I have all 3 variables, okay, that means that I need to go ahead and use the combined gas law. But the nice thing about the combined gas law, this is really the only one you need to memorize. If you can remember that, let's just take this bottom part away here. Oh, heavens. No. All right. We're going to switch up to this thing again. If you just have pressure and volume, okay, there we go. There's Boyle's law right there. Okay. If you just happen to have volume and temperature, just take out the pressure. And there's Charles' law right there. Okay, so combined gas law, if you can just remember the potatoes and vegetables go on the table, you pretty much got all you need. So in this first question, we have all 3 variables. So what we're going to do is we are going to use the combined gas law on this one. P1V1 over T1 is equal to P2V2 over T2. Awesome. So what is my initial pressure? Well, I see that that's 0.5 ATM. What is my initial volume? I see that that is 283 liters. And then what is my initial temperature? I can't use 25. I'm going to add 273 to 25, and that's going to give me 298. Then I'm going to go ahead and I'm going to do my final pressure is 1. My final volume, I do not know. And then my final temperature, can't do 100. Got to go 373 because I got to turn it into Kelvin. Now, how would we solve for this? just like we did with our other one yesterday, we are going to cross multiply. So what I'm going to do here is I'm going to do 298 times 1 times V, or X. I'm going to do 0.5 times 283 times 373. And the number I'm going to get for that is 52,779 and a half. So to solve for this, we just divide both sides by the smaller number. So I'm going to go ahead, boop, and, or excuse me, not by the smaller number. What am I thinking? This mouse is driving me crazy. I'm going to divide both sides by the number that is stuck to X. Just so happens to be the smaller number on this one, but not always. 298. And then that gets X by itself. And if I do 52,779.5 divided by 298, my V2 comes out to 177.1. And then we are looking for volume, so I need the unit to be liters. Very nice. And then let's go ahead and read the next one because it might be trying to be a little tricky here. A sample of helium has an initial volume, and I might have gone too fast on that. Maybe I'll give everybody a moment to catch up. Okay. If you ever need this pause, you just feel free to holler out and say, hey, can you pause that for a second? All right. So a sample of helium has an initial volume of 3,000 milliliters. I just most certainly do not like that number. I'm going to move it decimal 1, 2, 3. I'm going to call that 3 liters when the pressure is 500 atmospheres. And I do like that number. What volume does the gas occupy if the pressure goes to 300 atmospheres? Now, let's see. I have a volume and a pressure, and I have a volume and a pressure. Do I have any temperature anywhere in sight? I do not. So we can still throw in both of the other formulas. So just be careful and remember which one you have. So hopefully have your notes out. So which one do I need? If I have volume and pressure, that means we need Boyle's law. And that is P1 V1 equals P2 V2. Again, you won't have to write the law on the quiz. I just write that there. So you're like, where did she get that law from? So P1 V1 is equal to P2 V2. Oh, there it goes. Okay. I don't know if it's running out of batteries, but this thing, it's not working. So my initial pressure, it says a sample of helium with initial volume of 3 liters at a pressure of 500. So I'm going to multiply that together. Has what volume will it occupy if the pressure goes to 300? So I have 300 and then boom, now we want a volume. So now we can start to think. If I'm going to decrease the pressure on my gas, what should happen to the volume? And so the first thing we're going to do is we are going to take 300 or 500 times 3 and get ourselves 1,500. And then in order to solve for that, we do 300 divided by 1,500. And so V2 is going to get us 5 liters. So again, you can use any 3 of the variables. Like for this one down here, oh, we have an STP. You are given a sample of gas at 4 liters. So that's the initial volume. And its temperature, if it's STP, is going to be what for temperature? Good. 273 Kelvin. And the pressure is going to be what? 1 atmosphere. Okay, yep. What will be the final volume of the gas at 2 atmospheres of pressure and 30 degrees Celsius? Oh, I do not like that number. You better change that one before you get that in there. So you need to hopefully see that you are going to be using the combined gas law again on that one because you have all the variables going on here. So we want to make sure that you can solve. We have, 1 is my initial pressure. My initial volume is 4 liters over 273 for my temperature. My final pressure, we said is over here, is 2 atmospheres. The final volume is the question. And then I don't like this number, 30 degrees Celsius. So I'm going to add it 273, and that's 303. Go ahead and cross multiply. Give me an answer after you divide to solve for X. And then give me a unit on that final answer. There should be an answer key coming around so that you can get these all done. And I hope to be able to see you sooner than later, and we can get back to the demos and doing the lab and getting everything squared away. So if you need anything, please don't hesitate to email me or reach out, and we will hope to see you soon.